Welcome to the second edition of the eBiology Teacher Podcast. I'm Mr. Doc, and today we're talking about tools of the trade in biology. That is to say, how to use a compound light microscope. More specifically, what are its parts and functions, how to use it, and why we'll be using it. We're also going to talk about the SI system very quickly. That's something that most people are familiar with. Hopefully you've had some experience with it. But more importantly, we're going to talk about why it's important for scientists to have a common measurement system. And finally, we're going to talk about some things that are good and bad lab practices. Hi there. Good to see you all, or good to see you in particular. What we're going to do today is talk very quickly about microscopes. Hopefully you've all had an opportunity to use them before, and this should be a quick review for you. If not, feel free to watch this podcast as many times as you like. All right, so let's go ahead and let's get started. Because in biology there are so many things that are too small to see with the naked eye, we had to come up with a way to see things bigger than they actually are. Most common type of microscope that you're going to find is called a compound light microscope. And basically what that does is it forces light through a specimen, and then that light then passes through a magnifying lens, which makes the object appear larger than it actually is. Another type of microscope is electron microscopes. This is where a beam of electrons is actually passed through a specimen in order to generate images. Now, you will not be dealing with electron microscopes, despite the fact that they do provide a much clearer image and a much greater magnification, because they are incredibly expensive, and North Central High School doesn't even own one. As a matter of fact, there are a lot of universities that don't own one, so don't stress about that. What a microscope does is it provides us magnification, but we also have to consider resolution. Now, as you can see on your screen here, magnification describes how large something appears compared to how big it actually is. Now, in this picture, you see a picture of my dog Shorty. And what I've done is I've magnified that small area right here, and I've made it bigger. Now, what you need to note here is I have magnified that 5 times. Okay, so I have taken this picture and I multiplied it by 5. Now, what I have also done is I have reduced its resolution, meaning how clear it appears. You see, as I go up in magnification, usually my resolution starts to decline because I'm making something appear bigger. Then I have to start fine-tuning the picture. Now, the good thing about microscopes is that we can control both magnification and to some degree we can control resolution. That's why we have adjustment knobs. You see, when you get something into view under one power, you can magnify it greater by switching the lens to make it look bigger, and then you're going to have to use those knobs to improve the resolution. In other words, to improve how clear the object appears. Once again, magnification refers to how much bigger the object looks as compared to its actual size. In this case, this picture is 5 times larger than its original size. But we'll also notice that it's much clearer in the original, even though it's smaller, than it is here, which means we've lost resolution. The anatomy of a microscope goes kind of like this. Each part has a job. This first part up here is called the eyepiece. The eyepiece is where you look through, and the eyepiece generally provides about 10x magnification. That means that the eyepiece itself, just looking through the eyepiece, would make something look 10 times larger than it actually is. The arm holds the eyepiece and the objectives the correct distance from the specimen, which allows us to have a constant way of viewing the specimen. The base is where we will have the scope sit. In other words, it's kind of the big bottom part of the scope. And when you carry a microscope, you're going to have one hand under the base and one hand on the arm at all times. It is a two-hand job. Again, it's a two-hand job. Now, I happen to have a microscope right here. And as you can see, I'm holding it one hand on the arm and one hand on the base. The reason for that is if I drop it, I always have at least one hand on it. Don't start carrying it around like a purse or whatever, because then you're going to break stuff. And in my classroom, you break it, you bought it. All right? And unless you do a lot of biology at home, buying a broken microscope probably not an advantage for you. The last thing you see on here is the stage and stage clips. The stage is where we're going to put the specimen, and the clips are what are going to hold that specimen in place. So if you gently bump the microscope, nothing will really move. From there, we're going to take a look at the different objectives. Now the objectives are these things that are located right here under the eyepiece and that rotating nose piece. Okay, that rotating nose piece is what we call the thing that the objectives switch on. Now normally speaking, you have a scanning power, you have low power, and you have high power. Scanning power is actually the lowest possible power that you can get. Hold on one second, I gotta fix something here because you guys can't see everything. All right, hold on one second. Gotta fix it so you can see everything. We're gonna go 20. Uh-oh. Format. Hold on one second. I should have fixed this before we went. I didn't know it was a problem. Here we go. All right. So, in this picture here, we have the objectives. The scanning power is 4x. Now, here's something that we need to look at. If this eyepiece is multiplying by 10, and the scanning power objective is multiplying by 4, that's not 14, that's 40. 10 times 4 is 40. So if we look at something through the eyepiece and through the scanning power objective, which is always the shortest, then it's going to be 40 times its normal size. The next one is low. Now I know this is confusing. I get that. Low power is not the lowest power. You see, microscopes are kind of like Starbucks. What do I mean? Well, at Starbucks, a grande is the smallest thing you can get, but grande means large, right? A tall is also one of the, I don't even remember. That's why it's so confusing to me. So don't think about low power as being the lowest. Scanning, then low, then high. Okay, that's the order. That's the important thing. All right. Low power generally multiplies by 10, but keep in mind if you're looking through the eyepiece, which you're always going to be looking through the eyepiece, that's going to be 10 times 10, which is 100. And finally, the high power is the highest magnification on your compound light microscope. It multiplies by 40, which means 10 times 40 is 400. Now, on the microscopes that you'll be using in class, the red lens is going to be scanning power. The yellow is going to be low power, and the blue is going to be high power. Red is scanning, yellow is low, blue is high. Okay, that's just for the ones that you're using in class. And that's usually a pretty common thing. All right, and one thing that I also want to mention here, went too far. Don't forget that the total magnification of something is the magnification of the objective times the eye lens. So if you're on low power, the eyepiece is 10 and the low power is 10, so your total is 100. All right? Now, total magnification is, once again, how we look at how big we're looking at something. So if we take the eyepiece, and the objective, multiply those together, that's going to give us our total magnification. There are two parts of the light microscope that provide us with some with light. First of all, there's the light source, which is this lamp that's located underneath. That's very simple, and there's usually a switch on microscopes. Some microscopes even use a mirror to reflect light. We don't use it anymore. We use electric microscopes. The diaphragm, however, is this little disc, and you can barely see it, but it's this little disc right under the microscope. That changes the width or diameter of the hole that's under the stage, therefore controlling the amount of light getting through. Now, what is the big deal with that? Well, sometimes we want more light, and sometimes we want less. So we need to be able to control that. And since we don't have a light that has a variable intensity on it, we need to be able to control that some other way. So the diaphragm has differing size holes in it, and they get smaller and smaller. The smaller the hole, the less light that gets through. The less light that gets through, obviously a different view on the specimen that we're looking at. So that's what you want to look at. If for some reason you get into a microscope, you know the light's on, you can't see anything but black, check the diaphragm, because the diaphragm could be completely closed. All right. So back to the notes. Focusing is the next part. You have two major knobs on the microscope. You have a larger knob, which is referred to as the coarse adjustment knob, and you have the smaller knob referred to as the fine adjustment knob. Coarse adjustment knob literally moves the stage up and down. All right, this gets the specimen in position. Under scanning and low power, you can use the coarse adjustment knob. Never use the coarse adjustment knob on high. Don't even touch it. Don't even come close to touching the coarse adjustment knob because of a very simple rule. Most of the things that you look at are going to be on a glass slide. The high power lens is going to come very, very close to what it is you're looking at. And if, for some reason, you go too far and that lens touches too much, what's going to happen? Pah! All right? You're going to break the specimen. We don't want to do that. So never, ever, ever touch the coarse adjustment knob under high power. Don't even think about it. And never remove a slide under high power, because if you try to lift it up, it's going to break, right? So what's the rule of thumb? Always go back to scanning power. You're going to start at scanning power. You're going to end at scanning power. All right? Let's go back. The fine adjustment knob. Well, maybe your question was, well, if it's not in focus under high power, how do I adjust it? That's what the fine adjustment knob is. The coarse adjustment knob is just simply going to get it into position. And then finally, the fine adjustment knob is going to fine-tune that resolution that you were looking for. Again, the coarse adjustment knob should never be touched under high power because it can break the slide or specimen. All right, before we move on to measurements, I want to go over quickly this virtual microscope. Now, this is courtesy of the University of Delaware, and it is available on my website, mrdoc'sonlinelab.com. So just go to my site and go to Honors Biology. You should be able to find it, or to the related links page. Here we have a microscope. Now this happens to have two eyepieces. It's called a binocular microscope. Most of ours only have one. We have our coarse adjustment knob here, which is the large one, the large knob, and the fine adjustment knob, which is here. We have our diaphragm here and our light switch here. Okay, so what I'm going to do is I'm going to turn my microscope on, and all of a sudden you can see that the light is on. Yay. Now this one happens to have 4 lenses. Okay, it has scanning, low, high, and this is what we would call an oil immersion lens, which we won't be using this year. We won't need it. Now let's take this letter E, for example, and let's put that slide under. Now you see that little hole right there? The specimen needs to be over that hole. Now on our microscopes we're simply going to move them, but on this one it actually has this neat little dooflotchy where we can kind of position it where we want it. All right? And so what I'm going to do is click and click and click and click until that little black dot, which is the thing that I'm trying to look at, is right over the hole. So I have the specimen in position. I have the light on. Now I can look through my lens. Now this is something that you should not have to do, but in this microscope we have to adjust the binocular pieces so that they are within view. Now here's what I'm going to do. Coarse adjustment knob is here, fine adjustment knob is here. Notice that I'm starting on scanning power. Now I'm going to start tuning my coarse adjustment knob, and there I start to see something. Now if I go too far, it goes away. And this takes us to a little point. If I'm looking at a microscope and I'm tuning it, it's kind of like tuning one of those old radios that has the knob. You tune it and all you hear is static, and right? And then all of a sudden you hear, and here we go, and there it goes again. It goes away, right? Tuning a microscope is kind of like that. You tune it and you see it and then it goes away. So you have to tune back and forth until you get that nice, pretty view that it was that you're looking for. Now, the other thing I want to do here is this. This circle is called my field of view. If I go up in magnification, my field of view is going to narrow. So all I will see is this part right here. Well, if I want to see the whole thing in my field of view, I need to get it centered, right? So what I'm going to do is gently move my specimen right to the center of my field of view. And now I can go up in power. And now I'm on my low power lens. Now, notice if I change the diaphragm here, I'm letting more light through, and all of a sudden, it becomes a little easier to see. Okay? Just like that. Now, once I have it in focus under low power, I'm going to put it under high power. And there we go. I'm under high power. Now, let's see if I can get any more detail. See, I'm using the scanning power, or the fine adjustment knob to get the detail that I want. I can move it back and forward to get that detail that I'm looking for. Now, watch what happens if I hit the coarse adjustment knob. Oh, warning, it's not a good idea just to touch the coarse adjustment knob except under low power. Do you wish to continue? If I hit yes, what's going to happen? Boom. It's gone. Now I'm going to go back, and it's still there, but here's the thing. And this is something people get confused. If I say look at something under high power, you can't start under high power. You have to start at scanning, get it in focus, get it pretty and clear, get it right in the center of your field of view, up to low power. Get it pretty, get it centered, right in the field of view, boom, up to high power. You can't skip a step. You always have to start at scanning. Even if you're asked for high power, you always have to start at scanning, then go low, then go high. All right? Don't forget that. That's very, very, very important. So I'm going to play with one more here. Now, I'm going to go back to scanning power because that's where I belong, right? And now I'm going to put a new specimen in. This is an onion root tip. So let's see here. I'm going to center it. Centering it right there. And now I'm going to switch. I'm going to look in and look at that. Now I want to look at this area right here, right? So I'm going to need to center that in my field of view, just like so. Now, I can zoom. Nope. Uh-oh. Uh-oh. Fine-tune it just a little bit. Fine-tune it just a little bit. Now, this thing tells me this is the area I want to look at. So I'm going to go ahead and get that under view. Okay, that's red circle. That's what I'm supposed to be looking at. Boom. Right there. Now I can go up to low power. All right, use my fine adjustment knob to get it a little more focused. See how it's starting to get blurry again? See that little splotch right there? That's actually part of the slide, right? So I've gone too far. There we go. And now, once it's in focus, I can get it on focus under high power, which is, uh-oh. Now, I can use my fine adjustment knob to get it right in focus. Now I want you to notice the resolution is not great. That's because we are magnifying it way, way, way up there. All right. So hopefully that's a pretty good kind of crash course in using a compound light microscope. If you have any questions, feel free to ask me or play with that website. Go to my website, mrdoc'sonlinelab.com, and look for the virtual microscope. And that's a fun tool. Ooh. I can't get sorry. The virtual microscope is a fun tool to use. Get a lot of practice with it too. I think things start to make a little sense. Now, let's go on to another quick topic here. Scientists need to make measurements. That's how we communicate. But to effectively communicate, we need to uniform those measurements. If I'm talking about feet, meaning 12 inches, but you're talking about feet, meaning the size of your foot, and your foot's 9 inches, then we're never going to come up with the same answer. So we use the International System of Measurements, or SI. The standard measures are listed below. An additional benefit to having SI is that converting them from one form to another is easy because the math is all about dividing or multiplying by 10, which most people can do in their heads. 1 times 10 is 10, 10 times 10 is 100, 100 times 10 is 1,000, and so forth on. Using SI measurements means that you're going to speak the same language as other scientists. Now, you may say, but a foot is the measurement that I use, and that's not one of the measurements. The SI units are in meters. The United States uses the English system of measurement, which we're the only major country that still uses the English system of measurement, including the English who invented it. Why don't we change? Well, it'd be kind of expensive because then instead of selling gallons of milk, you'd have to sell liters of milk. All the road signs would have to be changed. Instead of saying 5 miles to Louisville, it'd have to say 2 point whatever kilometers. It's just a mess. So that's one reason not to change. But we do speak the same language when we speak the SI system. Now let's talk about procedures in terms of the lab. That's misspelled. The data that you get from an experiment is only as valid as the procedures you use. Common errors in lab procedure can have a huge effect on your outcome. So remember, control all your variables, which we talked about in the scientific method, and to make sure the only thing that is different is the variable that you're testing. Here's some common lab errors that I want you to avoid in my class. First of all, cross-contamination. If a specimen comes in contact with something outside, then the specimen may no longer work in the same way. For example, if we are looking at several different slides of different creepy crawlies like euglena and amoeba, if you accidentally put a pipette with amoeba in the euglena, then you might see an amoeba when you're hoping to see a euglena, and then you're like, I don't know whether that's a paramecium, and oh, there's a new word, head explodes, and there you go. So avoid cross-contamination. The other thing is, if you're testing the effect of one substance on another, and the two substances combine, you don't know what's having the effect. Is it this substance or that substance? So avoid cross-contamination. A quick and easy way to do that is make sure if you're using pipettes, use one pipette per sample. Don't go from one sample to another. If you're using tweezers or forceps, then use only one set of forceps per sample. Okay? In terms of mismeasurement, using incorrect measuring techniques can cause your data to be off or just plain wrong. So make sure not only you know how to measure, but you do it consistently throughout. And if you lack consistency, these small differences can make your trials that you've conducted very, very inconsistent and very wrong. So you need to do everything the same. It's not just what, but the how. And this is a pretty big point. If you measure something, and keep in mind, in biology, sometimes we're talking about very, very small measurements. So the smaller the measurement, the less it takes to mess that measurement up. So if you are looking at something that's a nanometer and you're off by 0.2 nanometers, that's a pretty big deal. That's a pretty big deal. So make sure that you measure correctly. And the final point I want to make is the lack of clarity. And sometimes if you make mistakes, it may be because the experimenter doesn't know exactly what you're doing. So before you start getting in a lab and start doing all the fun stuff that you get to do, make sure you know what you're doing, because if you're not sure, then you start writing down data and you're like, my data doesn't make sense. Well, that's because you screwed it up, not the data. It's not the data's fault. If you don't know what you're doing, there's no way you're going to get what you want to get. All right? That's simple, simple. So here are the objectives. Describe the function of a compound light microscope. Well, instead of doing that here, I'm simply going to refer you to the notes, but I'm also going to say, remember the virtual microscope. Not only will it tell you the different parts, but it'll also tell you what they do. And of course, the whole point of a compound light microscope is to make something look bigger than it actually is, and most times we'll be looking at things that we couldn't see with the naked eye. In terms of the scientific method, of course, we want to use, the scientific measurements. We want to use the same measurements as everybody else, so we're speaking the same language, and that's why we use SI, not only because that's the system used by scientists around the world, but it's also because it is easy to convert. And finally, make sure when you're doing a lab that you pay attention to what you're doing and make sure that you're consistent with your measurements, you're consistent with your procedures, and most importantly, make sure when you're doing something you understand why you're doing it. All right, that has been an eBiology Teacher podcast on tools of the trade, specifically microscopes. I hope it's helped, and I look forward to seeing you out here in cyberspace yet again.